All right, we're on page 477, working until 483. This is lesson 3. We're going to be working through the warm up, getting started, and activity 1 and 2. So this is analyzing lines of best fit. So we've had some experience drawing lines of best fit, writing the equations of it, but now we're going to analyze it. But we're going to start first off with the warm up here, and fill in these blanks here. So the first one, number 1, when a line has a positive slope, then as x increases, the y values, since it's positive, that means it also increases. Okay. When a line has a negative slope, then it's the same thing, right? As x increases, right? In this case, y increased, so I went up. When a line has a negative slope, then as the x values increase, the y value decreases. So the y value is vertical, so it goes down. So as you go right and up, that's positive. As you go down, right and down, right, that's negative. And then for number 3 and 4, we have a numerical fill in the blank. When a line has a slope of 7, as the x values increase by 1 unit, the y values, since it has a slope of 7, it increases. We're just multiplying 7 and 1. It increases by 7 un for units. And then number 4, when a line has a slope of 7, then as the x values increase by 5 units, the y values also increase by, you multiply 5 times 7, which is 35 units. All right, to maintain that same ratio, we're going to move on to getting started. So working within this new context or table. So this situation deals with age of a baby and weight. But the context, the Sanchez family has a healthy, happy baby named Mia. At each doctor's visit, the nurse records Mia's height and weight. The table shows her records from birth until she is 18 months old. Anyways, but this table, right, all this shows height and weight. We do have the weight here. Okay, so number 1, what happens to Mia's weight as she gets older? So as all this progresses, she's getting older here. What's happening to the weight of Mia or this baby, right? Is it increasing or decreasing? Mia's weight, and it's kind of apparent here, right? Not too much. We don't have to do any computation. The weight increases as she gets older, right? You wouldn't typically see a baby's weight decreasing. But an important thing to note here, and this relates to our topic of line of best fit, do you think she will continue growing at this rate? So, right, if you look at, you can try to subtract each one. Like, is there a constant amount? And do you think a baby will grow at the same rate? So for this, most likely not. Her weight will not increase. It'll still increase, but not at the same rate. So it will not increase at this rate. Right, at a certain point, it does kind of level off. So it should level off when she's fully grown. Right, it kind of plateaus at a certain weight. At a certain age, you kind of stagnate. Anyways, so we're going to be referring back to this a little bit later, but let's go into the next page, 479 on activity 1 of 2. Okay. So use the information about Mia's age and weight to answer each question. For number 1, use the data in the table to determine and analyze unit rates for Mia's weight gain. And number 1A, write a unit rate that compares Mia's change in weight to her change in age from these two ages, 4 months to 6 months. So unit rate, first of all, you know what, let's find from 4 to 6 months, and we'll talk about unit rate after that. All right, let me get rid of some of these. We're only looking at at this one here. So 4 to 6 months, right? We know that that is an increase of 2 months. And 13.7 to 17.0, right? You have to subtract that. Now, we can do this mentally. Like, what I like to do is figure out, right, 13.7, that's closest to which whole number? It's closest to 14. Right, so from here to here, 14 to 17, that's 3. And then from 13.7 to 14, that is 0.3. So the total distance here is 3.3, right? You add those two values, the 3/10 and the 3/1. All right, so let's go ahead and put that for this. So she gains 3 1/3, or 3.3 pounds in 2 months. Okay, now the unit rate is always where you want a denominator or numerator of 1. So what happens is we have to divide that. We'll have to divide 3.3 by 2. I'm going to plug into my calculator here. It is 1.65, and that is pounds per month. Okay, so just dividing it out. All right. And now we're going to compare that with a different amount. B, write a unit rate that compares Mia's weight change to her change in age from 6 months to 8 months. So let's go to that on the table. So that's the next part. 6 to 8 months, that's also an increase of 2. But what is this increase? 17 to 21, that is an increase of 4. So the dependent variable divided by the independent variable, this is 4 pounds, divided by 2 months. So what's 4 divided by 2? This is, on average, she's gaining 2 pounds per month. I'll put it like this. All right, so from 4 to 6 months, she was gaining 1.65 pounds per month, and now from 6 to 8 months she's gaining 2 pounds per month. Okay, so just be mindful of that. And then C, now we're going to compare those quantities. Did Mia gain weight faster from 4 to 6 months or from 6 to 8 months? Now we can just easily tell which one's a bigger number. Mia gained weight faster from 6 to 8 months, right? Because that rate of change, or that unit rate, is bigger, right? 2 is bigger than 1.65. Okay, right? We can put that here. 2 is greater than 1.65. All right. And then we're gonna plot this data on the next part, or it's already plotted for us. So now on page 480, analyze the scatter plot that shows Mia's age as the explanatory variable, right, that's independent variable, and her weight as the response variable, or the dependent variable. Or we can say that this is X and this is Y. Right, so we have age here, and then we have weight here. Now, for this, right, this is a scatter plot, right? It's a bunch of points that are graphed. Right, it doesn't form an exact line, but we can answer some of these questions from here. So number 2, do all the points in the scatter plot lie on the same line? What does this tell you about Mia's weight change as time changes? So is this a straight line? This is no. They do not form a straight line. All right, so this means that Mia's weight does not change at the same rate over time. So not a constant rate, not a constant rate of change. Okay. And then it says using a straight edge to draw the line that best fits the data. So I'm going to use my pen, but you're welcome to use a protractor, ruler, edge of the binder, whatever. Let's draw a line that best fits this. Now, if you draw a line like this, nope. It's got to be a line that follows the trend of the data, in this case, a positive slope. And it has to go through like the middle of these points following the trend. So if I take this line and I move this up, like I think this is probably something that might be a good line of best fit. Right, there's probably equal amount of points below this line, equal amount of points above this line, some points that are exactly on the line. But we'll leave it at that. Okay, so we did this. I'll just put a check mark here. And then number 4, we have experience, but we're going to write the equation of the line and identify the slope and the y-intercept of our line. So this just depends on how you drew it. So we need to find the slope and the y-intercept. Y-intercept a little bit easier to deal with. Let's say it's this point. Now if this right here is 10, half of that is 9. This has got to be like 8.5, something like that. I'll put it here. B is equal to 8.5. Now we got to find the slope of this. We can pick any points we want. I'm going to pick this point here. Right, it's got to be on the black line. And I'm going to pick this right here. It's not an actual data point, but it's a good point to use on the grid. Let's figure out our rise and our run. Okay. And every unit here is going by increments of 2. So this is 2, 4, 6, 8, 10. And our x-axis, this is also going by 2. So 2, 4, 6, 8, 10, 12. All right, and our slope. Our slope is rise over run, so 10 over 12. And then 10 over 12, what is that simplified to? Right, it's going to be it's a proper fraction, but if you plug this into your calculator, I'm going to round to the nearest hundredths place. We'll put 0.83. It's actually repeating 3, but we'll round that. So this is our slope. This is our y-intercept. Let's write both of those for the equation. Right, so if the equation is y equal to mx plus b, it's y equal to 0.83x plus 8.5. That is our equation. We'll use this equation to make predictions for information that we might not have. Okay. Oh, it does say identify, be sure to use your variables. Okay. All right, we're good. So this is telling us that this is our slope, how much we move. This is telling us that the Mia roughly gains 0.83 pounds per month. And since this is where we begin, this is telling us that maybe Mia weighed 8.5 pounds at birth when she was born. Just put when she was born. Okay, so we're going to provide some information for interpolation and extrapolation. But let's also identify here. So use the equation of the line to answer each question. Number 5A, approximately how many pounds did Mia gain each month from her birth until she was 18 months old? Okay. All right, so the information that we have here, I'll go to the table. Right, this whole information is for 18 months. So what we found for our slope is what's answering that question. So that is, we're going to say it's a little bit less than a pound per month. And we answered this approximately how many pounds did Mia weigh at birth. Right, according to the line that we drew, Mia weighed approximately 8.5 pounds at birth. All right, so this is the y-intercept of the equation. Okay, now we're going to use that to calculate the varying, her weight at varying ages. So for this first one, well, actually, let's read this. Use the line of best fit to predict Mia's weight at each given age if she continues to grow at the same rate. So number 2 years old. Now keep in mind we're measuring in terms of months. So instead of 2 years old, how many months is that? That is 24. So we're going to put y equal to 0.83 times 24 plus 8.4. All right, so this, for time's sake, we're just going to multiply this out using a calculator. So y is equal to, if you multiply, this is 19.92, so almost 20 pounds plus 8.5. And then if you add 8.5 here, this is 28.42 pounds when she's 24 months old or 24 years old. Okay. So that a 2-year-old weighing almost 30 pounds, I think that's probably like expected. But let's keep going here. So with B, we have 5 years old. That is 60 months. All right, so let's plug that in. Right, I know we've got some complex numbers, but hopefully using the calculator makes this a little bit easier. So 0.83 times 60 is 49.8, so almost 50 pounds. And we'll add 8.5 to that. So this is y equal to 58.3. So in 5 years, this girl is 60 pounds. Okay. Like maybe that's around like the expected value. So let's move on to, we're going to continue this trend and see for this for 18 years old. So this is 18 years old. She's graduating high school. Right. So you would have to multiply 18 times 12. So this is 216 months. Okay. So let's plug that in. It's going to be a big number here. 8.5. Okay. 0.83 times 216. That is y is equal to 179.28 plus 8.5. All right, and y is equal to 187.78. So for this, she might not weigh 187 pounds. Like maybe you can, use your own weight as kind of a barometer there. So what happens here is we talked about how the weight would typically kind of level off. You wouldn't typically grow at the same rate your whole entire childhood. So for D, do all the predictions make sense? We're going to put no here. And the reason for that is the weights might seem a little bit unreasonable here. Some 2-year-olds might weigh 28 pounds, but the other two are a little bit, let's say, more unreasonable. We'll say like many adults, not all, right? And there's definitely counterexamples too. Many adults don't weigh 180. We'll put 8 pounds. Right, they can, but our prediction might be a little bit off just based on how we drew the line. If I made that line a little bit steeper, then it would be even more so. So, number 7, what can you conclude about the accuracy of your model? We would say that the model probably is accurate for like the first 2 years. So we'll say it is accurate accurate when Mia was younger. But we'll say less so when she's older. And when we have data, it does inform us, but the more far off that data set is, or the prediction that we're making, we would need more information because there's more uncertainty there. So although the association is positive, as you age, you weigh more, maybe a linear equation might not be the best model. So going back here, if you look at all the blue points, I don't want to say like a line models this, maybe something that's more like a curve that kind of plateaus. Okay, that's a different function. You're not going to learn that in pre-algebra. This is called a radical function. So you'll learn about that when you get to high school. All right, anyways, so we talked about weight, and now we're going to go to height here, and we have data values to model that. So on page 242, number one says consider the relationship between Mia's age and her height. So what happens to Mia's height as she gets older? So as you can see, right, as she gets older, right, all these are increasing. What can we say about her height? Is it increasing, decreasing? Yeah, she's getting taller, right? She's getting taller because she's aging. So we will just say Mia's height increases, right, as she gets older. Right, and the same for, I would think, like predominantly like a lot of the students. So what we have here, we have a scatter plot that's taking those points from the table and graphing it on the coordinate grid. So number two, can you represent these data exactly with a linear equation? Right, with every single point, if I draw a line, wouldn't be on that line. So we'll say no. We'll say all points are not on a, we'll say, singular straight line. Right, so there is some variability to that. But that doesn't mean that we can't use a line to still draw something that models that. Let's say for this, maybe this is a line that kind of models it. I think we got some points above, some points below. I'm going to go right there. Right, maybe her height, if it continues past, right, as it continues past 18 months, maybe it'll follow along this trend. So let's go to number 3 and write an equation to model this. So again, the line that you draw is probably not going to be exactly the line that I draw, but let's go and put some things here. So the y-intercept, looks like we're going by increments of 3 here, right? 3, 6, 9, 12. So this right here, I think that's probably close to 21. But we do have to find values for our slope. So we can pick any one of these points. Let me pick, I will pick this point here that's on the y-axis. And let me I'll pick this point. This point is like somewhat close. So let's find the rise and the run. Okay, so the rise here, this is not just 1, 2, this is going by increments of 3, so this is increasing by 6. But our x-axis is going by increments of 2, right? 2, 4, so on. So this is 2, 4, 6, 8, looks like that's 10. Okay, so our slope here, right, we can put this as 6 over 10 as rise over run. And if you divide that, 6 divided by 10, just like with any place value, it really just moves a decimal point. So this is actually 0.6. Okay, so let's use those two pieces of information for the equation. We'll use this and this 21. So this is y equal to 0.6 x plus 21. And we'll answer that, some parts of this on the next part. Okay. So let's go and put that. Let's go and move on to the last page on activity 2. All right. Interpret the slope and the y-intercept. So the slope was 0.6. So what does that mean? Is that Mia's height increases, since it's positive, increases 0.6. This is in terms of inches. Right, I think it's in terms of inches. Yep, inches per month. And the y-intercept, we had 21. So we would say, right, for the y-intercept, this means that she was about 21 inches long at birth. Okay, so 21 inches, that's about like, right, a ruler, a foot is 12 inches, so she's almost like 2 feet. So, does that make sense as well as far as our predictions go? All right, for this, we're just going to do a couple. I'm actually just going to do A and B. You're welcome to do, A and C. You're welcome to do B as a you do. All right, but we have the same numbers here. Right, we have 24 for months. So this is y equal to 0.6 times 24 plus 21. All right, so we have a different equation. So 0.6 times 21 is 12.6. And if we add that to 21, this tells us that y is equal to 33.6. So she is, this is saying in 2 years, she is 33.6 inches. So 36 inches is 3 feet. That's a yard. So would we think that Mia as a 2-year-old is about a yard for her height? Maybe. Or maybe not. So for this, let's also go to 18. 18 we said is 216 months. All right, so y is equal to 0.6 times 216 plus 21. So if we multiply 0.6 times 216, that is 129.6, so really close to 130. But if we add that with 21, this is 150.6 inches. So that, if you divide that by 12, because there's 12 inches in a foot, this would make her over 12 foot tall. Okay, so 12 foot tall is, right, our classroom is about 9 to 10 feet tall. She would be towering over the classroom. Okay, right, just over the ceiling. So to answer D, do your predictions make sense? We're gonna say no. Okay. It might be reasonable for, right, when she's 2 years old to be about maybe a yard tall, a little bit less than that, but it's definitely not making an appropriate prediction when she gets older. So no, but we'll put we'll say 2 years old is an acceptable prediction. Right, so it's important to, right, if you have an equation, there are certain things that we can make good predictions on if they are linear. But as you can see here, it's not quite a line. You don't have to draw this part, but this does have some type of curve because, like we said for weight, right, it does plateau. So height does plateau. You don't just keep growing taller and taller and taller. And like, I don't know. There's certain students in this class that just aren't going to grow, but also some teachers like myself. All right. So number 6, what can you conclude about the accuracy of your model? Right, just like what we put for D, the model seems to be accurate for the first 2 years, but not beyond that. So we'll say accurate for 2 years old and younger. But after that, right, it's not a linear trend. It doesn't have this constant rate of change. So from there, we're gonna end it there. We'll get to activity 3 in the next time.